Join us as we explore one of neuroscience's most fascinating discoveries. Memory isn't a recording. It's a story your brain rewrites every single time you remember. Think memory is like a video camera recording your experiences? Think again. What you're about to discover will change how you learn, think, and trust your own recollections. Let's start by destroying a common misconception about how memory works. Most people believe their memories work like a video camera, faithfully recording events that can be played back exactly as they happened. But this is completely wrong. Your brain doesn't record memories like a camera. Instead, it does something far more complex and fascinating. The reality is that memory is reconstructive, not reproductive. Each time you remember something, your brain actively rebuilds that memory from scattered fragments. Let me ask you this. How different is memory from a recording? The answer will surprise you. Here's the stunning difference. A recording stays identical over time, but your memory changes each time you recall it. It's like a game of telephone your brain plays with it. Now let's dive into the neuroscience to understand what's really happening in your brain. Memory formation happens in 3 distinct stages: encoding, storage, and retrieval. But here's where it gets interesting. We can express memory as a function of encoding, storage, retrieval, and importantly, context. Context is the secret ingredient that explains why memories change. Information flows from encoding to storage, which happens in distributed networks across your brain, and then to retrieval, where reconstruction happens. During encoding, neurons fire in specific patterns. These patterns represent the experience you're having right now. Your brain contains approximately 86 billion neurons. That's 86 times 10 to the power of 9 neurons. And these neurons form about 100 trillion synapses, or 100 times 10 to the power of 12 connections. This massive network is where memories live. Here's a simplified view of a neural network. Each connection can be strengthened or weakened, and this pattern of connections is your memory. Let's examine exactly what happens during memory reconstruction. When you try to remember something, your brain doesn't play back a recording. Instead, it reconstructs the experience from scattered fragments. What exactly happens during this reconstruction process? Your brain gathers scattered fragments from different brain regions, reassembles them in the reconstruction zone, and outputs a memory that may differ from the original. Several key factors influence how reconstruction happens, and these explain why memories change. First, your current emotional state colors your memories. If you're happy now, you recall past events more positively. Second, recent experiences blend with old memories. What happened yesterday can literally become part of your memory from years ago. Third, social suggestions reshape your memories. If someone tells you something happened differently, your brain may incorporate their version. We can express recalled memory as the original memory plus changes from emotion, context, and suggestion. This is why eyewitness testimony is so unreliable. Let's look at groundbreaking research that proved memory reconstruction is real. Psychologist Elizabeth Loftus conducted a famous car crash experiment that changed how we understand memory. Participants watched the same car crash video. Just changing the word from hit to smashed increased speed estimates by 7 miles per hour. A single word changed their memory. The difference was 7 miles per hour, a 20% increase, caused by nothing but a word change. Even more striking, a week later, 32% of the smashed group reported seeing broken glass in the video, even though there was none. False memories were implanted through nothing more than a suggestive word. This is memory reconstruction in action. Let's quantify how memories fade and change over time using mathematical models. In 1885, psychologist Hermann Ebbinghaus discovered the forgetting curve by testing his own memory thousands of times. Memory retention R equals e to the power of negative t over s, where t is time and s is memory strength. Here's the forgetting curve. You retain 100% initially, but drop to 58% after just 1 day and only 25% after a week without review. Can we fight this forgetting curve? The answer is yes, through spaced repetition. Each review increases memory strength. New strength equals old strength times 1 plus alpha, where alpha is the learning gain. With spaced repetition, each review boosts memory back up. The key is reviewing just as you're about to forget, creating a staircase pattern of increasing retention. Let's walk through a concrete example to see reconstruction in action. Imagine your 10th birthday party. Cake, friends, presents. Let's see how this memory changes over time. At age 10, the memory is fresh. You remember specific details: the chocolate cake, your friend's red shirt, the weather. By age 20, the memory has changed. Some details are gone, others slightly altered. Was the shirt red or blue? You're not quite sure anymore. By age 40, the memory has reconstructed significantly. New elements may appear that weren't there, influenced by photos, stories, and other birthdays. Memory at 40 does not equal memory at 20, which does not equal the original at age 10. 3 different versions of the same event. Understanding memory reconstruction has profound implications for learning, justice, and daily life. In law, eyewitness testimony is far less reliable than people think. DNA evidence has exonerated hundreds of wrongly convicted individuals. Studies show that in DNA exoneration cases, about 73% or 0.73 involved mistaken eyewitness identification. That's 3 out of 4 wrongful convictions. A witness's reconstructed memory can point to the wrong person entirely, even when they're completely confident. Confidence and accuracy don't correlate in memory. Now let's apply these insights to become better learners and thinkers. Strategy 1 is active reconstruction. Don't just reread your notes. Close the book and actively reconstruct what you learned. Why is active recall more effective than passive review? Because it mimics the reconstruction process. Passive review creates weak memory traces, just one pathway. Active recall creates multiple strong pathways, making retrieval easier and more accurate later. Research shows active recall produces learning gains about 2.5 times greater than passive review. That's a 150% improvement. Strategy 2 is spaced repetition. Review information at increasing intervals to fight the forgetting curve. Research suggests optimal intervals of 1 day, then 3 days, 1 week, 2 weeks, and 1 month. Each review strengthens the memory. Here's spaced repetition visualized. Each review shown as R1 through R5, with increasing strength bars, creating permanent long-term memory. Strategy 3 is elaborative encoding. Connect new information to existing knowledge to create richer memory traces. Elaborative encoding creates multiple links between new information and existing knowledge. More connections mean easier retrieval and more accurate reconstruction. Let's explore how to build mental models that account for memory reconstruction. First, accept that your memories are reconstructions, not recordings. This humility prevents overconfidence. Second, cross-reference important memories with external sources like photos, journals, or other witnesses. Your brain uses all available information to reconstruct memories, including external sources. By cross-referencing, you reduce the impact of memory biases and improve accuracy. In conclusion, understanding memory reconstruction is crucial for learning, justice, and our understanding of ourselves.